This video we will be explaining everything that there is to know about the internal block diagram, which is one of the structural diagrams within SysML. So SysML has 9 different diagrams: activity, sequence, state machine, use case, requirement, block definition, internal block, package, and parametric. And we will be focusing on the internal block diagram here. So the prerequisite is that you know how to make a block definition diagram. We have a whole video on the block definition diagram. It's basically building out your composition or your structure of your system, but then you would jump into the internal block diagram, and you have some text here from the Practical Guide to SysML, a good reference text to explain the internal block diagram. So you can pause the video and check that out. But an example of the internal block diagram is how to interconnect parts. So these are parts, and it shows the flow between the parts. And then we have ports here. So we'll look at several different examples and break down those examples. So I'll quickly mention the iPhone connecting and charging to the wall outlet example. So for our block definition diagram, here's our context, charging context. We got the iPhone, charger cable, charger box, and the wall outlet. And so then you would create a diagram, create diagram, IBD, internal block diagram. I'll select that, but I've already got it already created there. So I could double click here and it would take me to the charging context, or I could find it within the containment tree. Notice I've got multiple different IBDs within this charging context. That is completely fine. They're just showing different detailed views. So you can choose to show like a more zoomed out view, as well as having other views that are more zoomed in. So right now I've got like a hyperlink. So if I double click this, it goes to that zoomed in view, and you can just add the hyperlinks by creating this active hyperlink to that other view, the iPhone charger cable detail. iPhone charger cable detail. So you can just manually add that there. Another thing that you can do, we have a video that is dedicated to this exact example, so I'm just kind of jumping through this quickly. But some things we didn't mention in that video was that if you select one of the linkages or connections, then you can hit this minus button, and it will start to show you a different layout there. So you can just make all these small, and you can see that there's 8 connectors between this port and this port. You can also just do the minus again, and it will charger port male of 9, and then charger port female, and then you can zoom back in. And sometimes the formatting gets a little wonky, but you can get back to where you were. I'll just Control Z my way back, but that is a cool feature. And then what these are signal flows. So these are signals which are in our signal package that you see here, and we have added these signals with a direction on this connector, and you can toggle them on and off, and you can see it go on and off there. And you can add multiple different signals within one row if you please. There's a lot of options here. A couple more things to note. You can create this Whitebox ICD table that you're seeing here, and this tabulates all of the connections, both the pinout and the connector level connections between the part properties that you saw on the previous ICD or IBD. So it's showing these are the connector level connections, and then if you zoom in, these are going to be the pinout level. So for this particular breakdown, we decided to have both connections. So that's why you saw when I minimized all these earlier, you saw it said 8, but then when I minimized it a third time, so this would be, so if I minimize it again, it shows 9 connections. And the reason that is because it's got the 8 pinout connections and then the 1 connector level connection to make 9. So that's just a personal preference. You can just choose to do just the pinouts, and that's totally acceptable. The thing is, like right here, this would be the connector level row, because it's got all of these things going across the entire connector. And something like this would just be a pinout level view. So it's kind of a personal preference. So the ones that are big are going to be connectors, and what I mean by big is have multiple inner proxy ports within them, and then like this one right here, for example, is just going to be a pinout. So you can actually make this ICD table by just right-clicking, create diagram, and you just type in white for Whitebox ICD. You just click that, and it literally just makes it automatically for you. You just have to be in the right context, which is the charging context for this. So super, super easy and helpful. Moving on, if we made another block and just called it extension cord, and we want it to be a reference property, so we create like a directed aggregation relationship, which creates a reference property with the R there instead of a part property. So if I just open this up, it says reference property. If I then go into the internal block diagram and I want to see that, I can just hit this and then reference property. And you'll note that the reference properties always have that dotted line, while the part properties have that solid line. And you can do your normal connections as you please. We won't spend any time in this video discussing the difference between proxy ports and full ports. We've got a whole another video which is dedicated to that topic. We've used proxy ports throughout this video. Just know that proxy ports are typed by interface blocks and full ports are typed by normal blocks. In this example, we have multiple different tiers of abstraction. So we have the toaster, and the toaster would be inside the kitchen, and the kitchen would be inside the house. And you could go up even further to a bigger Russian doll, or break down the toaster into its subsystems and break that down into the smaller Russian doll. The intention here, we have a whole video dedicated to explaining this, but we're focused on IBDs. So if we just look at the toaster, BDD, we have the inside the kitchen, we have the toaster and bread. The toaster has these elements inside of it. So once we make those elements, we would go inside of the toaster block and create an IBD, which you see here. And so again, these are elements of definition. These are blocks. These are not part properties. These are the part properties called out: the heating element, the power supply, frame, complete circuit. You can see the part properties underneath your toaster block in your containment tree. Here are your part properties. And then on your white box toaster example, your IBD, you're seeing the part properties. So if you click on this or right click and do select in containment tree, you'll see that that's a part property. So this context is the toaster context. So the frame is essentially the outside of the toaster itself. So these are the inputs and outputs to the toaster, and then these are the part properties within. So if we want to just go up a level to kitchen, and we would see inside of kitchen, we have our toaster, our coffee maker, and our blender. These are some of the kitchen appliances that we might find in a kitchen, and our kitchen has these three blocks. We also have a toaster black box. So this is at the kitchen level, so it's at a level higher than the toaster. So if you're trying to look at the black box view of a system such as the toaster, you have to go up to the toaster context, which in this case would be the kitchen. The kitchen in this case is the frame of the diagram, and we're actually hiding the other elements that are within the kitchen, such as the other appliances, and you can show them by just hitting display and then part properties, and you see your blender and your coffee maker. That's not what we're trying to show in this diagram. We're trying to show how the toaster is toasting bread and what else it's connected to. So the toaster is not really connected to the blender, so that's why we are not showing the blender or the coffee maker here. We're trying to show what everything is affecting or connected to the black box toaster. Black box meaning you don't see what's inside the toaster or the system, you just see what's going in, such as power, and what's coming out, which is heat. If we go back up to the kitchen IBD, we see this fork, which means you can double click it and go inside of it. So it's like you go from a zoomed out view of the entire kitchen to a zoomed in view of just the toaster. Now another thing you can do is you can go up here and show them all on one by going to this display and then go to display parts and ports, and now you can jump into the toaster and start adding these parts within it. And now you're seeing the subsystems of the toaster, and you can actually drag these out of here, and there's a different way to represent them. You can represent as a shortcut, which is what we're going to do, and it has this dot notation, toaster dot complete circuit. So it's saying that the complete circuit is within the toaster. It's just being shown here. So you can put it back, represent a shortcut, and now it doesn't have that dot notation. So two different ways to show the same thing. Note that if we find this in the containment tree, that complete circuit right here, if I drag this here and then do change owner, it's going to move this part property from underneath the toaster to a kitchen level part. So if I do that, change it, you see that it disappeared here. It's now within the kitchen. The complete circuit toasting lever, start toasting lever, is within the kitchen and not within the toaster. So that is like incorrect. If you don't have the dot notation, like this is not the right breakdown anymore. So if I drag this back over here to toaster, what's going to happen is it's going to turn red. It's because it's being shown incorrectly. The part property complete circuit is not owned or inherited by the block kitchen. So you can either delete it here or just move it back to here, and now it will stop being represented with the red path around the rectangle. You can also start showing the proxy ports and connectors within the toaster context, and that's what we just did. You just hit those three little blocks and it will show all of the ports. These are all just proxy ports, but it would show the full ports as well if there were, as well as the connectors between them. You can note it's kind of hard to see here, so that's why I had two different views, this kitchen level view and then the zoomed in view. But know that the lines on this screen are now going to correlate with the lines on this screen. So if I go and delete this line between the power heating element from the power supply and the start toasting lever, if I find it in the containment tree right here and hit delete, if I then go inside of here, it is now gone from here. So that's good to know that, you know, they are the same connection. So I'll just go ahead and add that back and then go back to this level. You're not seeing it right now, but it is happening behind the scenes. So if I just hit these show ports, display all ports, and you see that this line then came back into the picture. What I'm going to do is clean this up just a little bit so that I can show the next part of the example. So I'm going to make this toaster bigger. So we're going to select multiple of these connectors by holding the shift button to allow you to multi-select, and then we're going to do Alt B, which is going to find those in the containment tree. You could also right click and then do select in containment tree. See those two? So we're going to delete them from the model, so they are out of the entire model. So even if I jump into here, they are gone. Jumping back to our example, we have this handy dandy tool up here, which is Autowire parts. And then you see that it auto-wired the parts. You can click OK here and then zoom out, and it will highlight the ones that it auto-wired for you as yellow so that you know to go back and make sure that it is correct. We know it's correct, so you would actually hit that confirm connector button there, which makes it go back to black, and it makes the little hazard icon go away within your containment tree. Since there's one still left, it will then show it. It will also show it down in your zoomed in view as well. And to get those wires to show back up, you can just show the proxy ports and they'll pop back. So I'll do that for this one as well. And now it's popped back, but notice this one will turn orange. There we go. It just took a second to get it to turn orange there. Let's say that it was incorrect and that connection was wrong. We would hit delete connector, and now it's gone there, as well as the upper level right here. It's not there. Another feature to note, let's say that this connection is also out of the model, so it's gone from the model. Let's say that this proxy port is gone, so, and we'll just make a connection between the heating element, which is a subsystem of the toaster, all the way out to the slice of bread. What we can do is hit the hit this linkage right here, and then do delegate ports, and it will automatically create that port that is between the two between bread and heating element. That can be really helpful to quickly make ports that are typed by the correct interface block. So the limitations to these auto wirings is that you must have the ports typed before you hit that auto wire. Otherwise, it won't know how to find it. So what it's doing is it's looking for connections that, or it's looking for ports that don't have connections with the same type. So like wire to wire. That tilde is the reverse. So like the inverse. So it's like this would be the plug end, and then this would be the receiver end, for example. So if I just hit auto wire parts, it's going to know to do that there because they have the same type there. But if I were to type it with something else, so I'll just create an element interface block, wrong interface, and then I put that over here, and then I hit that auto wire parts. It's saying no matching interfaces found because wire is not the same as this wrong interface, so it doesn't know how to connect them. More of these tips and tricks can be found in the help, other documentation, and then SysML plugin user guide. This is a 700-page document, but you can see, like right here, we explain the delegate port, and if you have any more questions about it, then you can refer to this guide, as well as some of the other detailed tips and tricks that we talked about in this video. So before we start simulation and simulating behaviors on this IVD, we need one more piece of information, which is the flow properties. So I have added these flow properties to each of the interface blocks, and each of the flow properties are typed by a signal, that power signal in this case. So this is the wire, and it is typed by the power signal. So if I were to change it to something like heat, which is our other signal, you'll see that now it is incompatible because we have a power signal going over something, the wire, that only will accept heat. So the incompatibility is nice to know. So I'll just change it back to power. The way that you would actually create this, create element, interface block, new interface, and then create element, and then flow property. In is inward, out is outward, and so in out is both. So out, you see the arrow going that way. If I were to change this to in, the arrow will change directions, and you'll have flow incompatibility again because the power is going the wrong direction. But you saw that they changed directions there. So I'll change it back to correct, out, and then you just drag the signal onto the flow port and to type it. Now what we're going to do is create some behaviors so that we can simulate them. So the power supply, it will receive power. When it receives power from this interface, it will then send power through that interface. So we're going to model that with just an activity diagram. So I can right click, create diagram, activity. So the important thing to understand is it's taking power and then it's sending power through the power heating element interface. So it'll receive the power there, and then it will send the power. And this is the important part. We need to know what port it's sending it on. And that was the power heating element. So we have to select that port, and now what it's going to do is it's just going to repeat. So I'm going to show this activity on this diagram as well. And now, instead of having power come from some other source. I'm just going to manually, the user is going to input it. So when I push play, now this activity has started. You can see this activity started here. The reason why this activity started is because this is the context which I started, so it's going to start any of the classifying behaviors. And this power supply is the only one with a classifying behavior. So if I look for a classifier behavior, right here you have power supply, but the other ones don't have that, any classifying behavior. So now it's waiting for the power. So what I can do is I can actually provide power myself, the user can. So, and you saw that power got sent to the start toasting lever. So I went ahead and scaled it for the other part properties, added the behaviors. So when we run this, 3 activities start because 3 of them have classifying behaviors. And so now I can go into the power supply and I can provide that power, and now you'll see it cascade. And I could also start with the start toasting, provide power there, and you'll see just a second too. Additionally, we created this activity diagram up here. This is for the toaster, so this is at a higher level. So when we run this, it's just going to loop and send this initial power command. So we have all 4 of them start, it's waiting 4 seconds, and it's going to send the command through that, and then it's going to repeat. So it's waiting 4 seconds and it's going to send it again. You could also do a similar thing where you remove that and wait for the user to send the power command. So we'll simulate that. So we're running it. So now it's just waiting for the user to send the power command here. What we can do is right-click toaster, create sequence diagram, and now you'll see that when I send the power command, it will create a sequence for the entire chain of events, like that, which is pretty cool. So it automatically creates a sequence diagram for you. Additionally, you can find where that sequence diagram is, and you can paste it into the toaster, and we'll just what we can do is actually just remove all this, because this happens automatically, and so all we want is the user setting the power button to the toaster. So that's all that's left there. And then you can right click it, simulation, run with context, now that it is in the context of the toaster. Push play, and it sends that power signal and then kicks it all off. So I could even do it again, to do it twice. And I'll put some time in between there. So it ran the first one, and it ran the second one.